Hello everyone, welcome back. So this is our third lecture in the course, Drug Use and the Brain, Unit 1. There will be 4 units that we'll spend on the brain and how drugs affect the brain. So that'll span the next 2 weeks. We're going to spend a little more time on it than your book does, just because I think it's interesting, but more importantly, I think it's significant. Um, if we're going to talk about individual drugs in the coming weeks, it's important for us to have a foundation for how the brain works. So when we talk about how a drug works chemically, we'll understand what we're talking about. So we'll spend the next couple of weeks on drugs and the brain. If you've had a neuroscience course like biopsychology, this should be familiar territory for you. If you haven't, if it's been a while since you've had biology or chemistry, some of these concepts may be familiar, some maybe you haven't heard in quite some time. So you may need to go back to the book or back to this lecture and look over it a couple times. And as always, you can email me or post questions to the discussion board if there are questions that you have about course content, because there's something that's a harder concept in your opinion. So we can talk about that via Blackboard or via email, either way. So before we get to the brain, a little housekeeping. So first, the discussion board. Almost everyone in the class participated last week, so that's great. Some very thoughtful comments. So well done, keep that up. As I mentioned before, the first couple of weeks we're going to have comments on the discussion board be based individually, so everyone posts their own comment. And after a couple of weeks, after everyone's comfortable with the discussion board, I'll break you into groups and you'll collaborate on your responses. There was a question last week that I received about the discussion posts as an assignment. So there is a heading under assignments that talks about participating in the discussion board. You don't actually have to submit an assignment that way. You don't have to copy in the text of your comment and submit it. That's really just in there so you can see the rubric, so you can see what the expectations are for your responses to the discussion board. So there's no need to submit anything via the assignments section of Blackboard. Once you post to the discussion board, I'll see that and that'll be good enough. Also, there was a question that I got about replying to the main thread of the discussion question or replying to others' comments. You can do either one. So if somebody posts a comment that you think is good and you want to elaborate on it, that's great. If somebody posts a comment and you disagree with it, you can reply to it that way as well. Or if you just want to respond to my original question, if you have something new that you want to say that no one has commented on yet, you can do that too. You can just reply to the original post. Any of those is fine. Remember, the important thing is just that it's relevant to the discussion, that it adds to the discussion, that someone hasn't said it before, and that it's clear. Okay, so as for last week's discussion topics, one of them was about drug regulation and religious freedom. And by the way, the class, as a class, you contributed very evenly to all 3 topics, so that's good. I hope that those topics will be interesting to the whole class, and so obviously every one of you thought a different comment was interesting. So we got a lot of comments in each topic. The drug regulation and religious freedom had some interesting comments. So some of the comments, most of the comments I would say, indicated that they were in support of allowing, at the very least, Native American populations to use hallucinogens as part of their religious practices, and many, of course, advocated allowing all the members of the population to do so. So there are some interesting and complex points about this topic, which is why I posted it. Whenever I respond to people's posts in this forum, my goal is not to come down on one side or the other and say, oh, this side really won the debate. These are complex issues, and the fact is there is no obvious solution, which is why I make them discussion topics. So for this particular issue, one of the complexities is that we're dealing not just with a subsection of the population, but with a sort of special subportion of the population. We have a group, Native Americans, that didn't really opt into membership in the United States. And this is different from someone who was born an American citizen, always has been, or immigrated and became a citizen. So one of the key points is whether or not this constitutes a special population and should be allowed certain privileges, whereas the rest of the population isn't. Some people thought that was fair. Some people thought that was unfair. And there's no easy answer for that, but it's an issue to consider. Um, One of the dangers people thought was present uh, was that people would falsely claim they were a member of a religious group if if a particular kind of drug was limited legally to that particular population. And of course, if a certain segment of the population has access to a drug legally, then what does that do to availability for the rest of the population? Does that increase the availability of the drug to everyone else? And is that a negative? Is that a positive? It's hard to say. Also, another common comment was that the members of the tribe the members of the religious group that were using this drug would be experienced and would be less susceptible to abusing it. Now, I don't know if that study has been done, whether that's true or not. It's certainly plausible, and it may differ from one drug to another. One of the interesting things that was not mentioned as much, I think, is that things like religious freedom aren't, of course, absolute. They're very important, and they are guaranteed by the Constitution. But all of these things like religious expression, freedom of speech, um, these are true up to a certain point. And in fact, this has been the case for a number of our freedoms, that up until the point where it harms other people, that's where that freedom ends. So, for example, our freedom of speech is not extended to, for example, yelling fire in a crowded theater. That isn't covered under freedom of speech. Why? Well, because it presents a public hazard. And so that's one of the hard things about this debate is assessing whether this drug represents a harm. And what do we do about that? So is it harmful enough? Is the threat great enough that it represents a risk to the public, a threat to the public? In which case, does that justify curtailing religious freedom in that particular case? And if you say no, that's, again, this is a complex issue. Um, but for example, our religious freedom does not extend to human sacrifice. So you're not allowed to do that. Um, and again, this is obviously a less overtly harmful and probably a less harmful overall issue, but it's a matter of degree. So in this class, I'll every now and again remind us that few things that we deal with are black or white. There very few things are binary in that sense, yes or no. These things exist on a spectrum, and especially given the range of drugs that are used in religious ceremonies, some may be more harmful than others. Some may be riskier than others. So how do we take that into account when all of them are part of religious ceremonies? So how far does religious freedom go? Uh, do Native Americans constitute a special population and therefore deserve special privileges? These are hard issues, but it was very well discussed in the forum. The second one was the risks of marijuana use, and there were a lot of personal stories about friends, family members, uh, personal experience with marijuana. I want to say first off that is great. That is always interesting to throw in your personal experiences. Only do that to the extent that you're comfortable with it. My goal here is just to elicit some that's illicit, not illicit, uh, personal experience that you're comfortable sharing. So don't talk about your own drug use if you don't want to do that. So that's first and foremost my point here. Second is that a lot of people mentioned the usefulness, the positive stories that they've encountered regarding things like medical marijuana especially. And there was also a common opinion that marijuana is not as harmful as other drugs. Uh, and that is probably true, certainly compared to other illicit substances, that is probably true. Keep in mind, though, and I'll come back to this again and again, that we want to avoid uh, equating drugs with illicit drugs. So when we say drugs, That just means any chemical that really affects the body. Here we're talking about psychoactive drugs. So these are drugs that affect the brain in some way. So we want to really concentrate on the fact that drugs don't necessarily mean illicit drugs. Um, so I want to make that clear. Another common sentiment was equating drugs and illicit drugs with escapism, and how that was as a negative, because as we all know, escaping a problem through drugs doesn't really solve the problem, and that's a fair opinion. Um, One thing to keep in mind, of course, is that not all drugs are used for escapism. So when we say things like we shouldn't use drugs to escape reality, um, there we're talking about a very specific subset of drugs. So we are all most likely drug users. We've all used drugs, even if it's something as simple as aspirin. And so that alleviates pain. That is a psychoactive drug because it changes our perception of our bodies and the outside world. Uh, so that is one thing to keep in mind, is that not all drugs, and the term drug use doesn't necessarily mean escapism, and also that, as we'll see, drugs have a variety of effects, and some of them may alter our consciousness, but some effects may relieve pain. They may reduce anxiety. And so the question becomes, well, how do we define escapism? And this is one of those things that's not black or white. So if someone reduces the amount of pain they feel, are they escaping reality? Or if someone reduces the anxiety they feel, are they escaping reality in that sense? In reality, they're anxious about something. Once they use drugs, they're less anxious. So they are, in some sense, changing their perception of reality. Uh, but that's not the same thing as saying they're cognitively impaired. So we should be careful about drawing that line and about making the distinction that drug use is about escaping reality. Um, and it's not to say that it isn't in some cases, but that may be a side effect of the drug, that somebody is using it for another purpose, um, or it may be that it does that to a certain extent, but how do we decide when drug use qualifies as escapism? And then finally, the last topic was about the pros and cons of a drug, discovering the positive and negative effects. And there were a lot of comments about this, about why you all thought that the positives were noticed before the negatives in general. Not always the case, but often. So one of the major factors is, of course, expectations. And we talked about that already, that when you expect a certain effect from a drug, usually it's a positive effect. No one takes a drug looking for those negative effects. So if you're expecting pain relief, or if you're expecting euphoria, often these are the things we notice. And this plays into a psychological effect called confirmation bias, where we notice the things that we already expect to notice, that we want to notice, and ignore the other stuff. There are also things like the goals. What are we trying to get out of using the drug? So what do we expect? What are we trying to do? And we tend to emphasize those aspects. Um, Another issue, of course, is that the negative effects in certain cases just take longer to show up. So the pain relief is immediate for things like an opioid, the pain reliever. But the dependence comes later. So that's another issue, is that often the negative consequences are long-term, whereas the positive effects are short-term. And we tend to overemphasize those short-term positives. Of course, one of the issues that wasn't talked about as much is just the technology we have at our disposal. So it took a long time for us to realize how harmful in the long term tobacco was, not necessarily nicotine, but tobacco, um, even though we've been using it for hundreds of years. It wasn't until the late 1800s and early to mid 1900s that we realized the long-term effects like cancer, because that takes decades to expose. We have to use statistics to analyze the long-term data. And earlier in history, we just didn't have that at our disposal. Uh, so those were all great discussions. So thank everyone for contributing. Finally, coming up is paper number 1. I say coming up; it's a month away. And this week I will post what the guidelines are for that paper. So keep that on your radar screen. I'll post an announcement about that and put it under assignments. Okay, so for today, we're going to look at drugs and their effects on the brain. We're going to look at that today and really for the next couple weeks. Today we won't talk about drugs, and even the second lecture of this week we won't talk about drugs. We're just going to talk about the brain and its normal state of affairs. So we'll begin talking about neurons, which are brain cells. We'll move on next time to synapses, which are connections between neurons. And then finally, we'll talk about the brain as a whole. So we're going to start at the smallest possible scale and then move up from one brain cell to a couple of brain cells, and from there to the whole brain. So in this session in particular, we're going to talk about different cells in the brain. There are multiple types. And we're going to learn about the environment that neurons inhabit. So what is it like to be a neuron, so to speak? How does a neuron work? So specifically, how do neurons transmit information? And the environment they inhabit is a big player in that. And we'll understand what that means here in a minute. So first, we're going to introduce the brain. So we've probably all seen a picture like the one on the right. But what this picture does, this diagram does, is go down in scale. So you see the whole brain, then we go down to an individual brain cell, and the brain cell has these tiny projections that we'll talk about, and those tiny projections connect to other neurons, and they have tiny molecules embedded in them, and these things all have a part to play. So we're talking about the central nervous system. So this is the brain and the spinal cord. We'll talk about the peripheral nervous system later. And this week we'll focus on neurons, the individual brain cells. And the neuron is the basic unit of the brain. It's the basic unit that processes information. And as you might imagine, for a human brain at least, there are lots of them. In fact, you've got 100 billion in your brain, give or take. So these cells connect to one another, so you can imagine the sheer number of connections is really quite large. And that's what allows our brain to process as much information and process it as deeply as it does. So basics, we'll talk about neurons. So first off, what is a neuron? Well, a neuron's a brain cell. And so we see a diagram of it here at the top. And so it's really quite small. The size of a neuron can vary from one type of neuron to another, but they're microscopic for the most part. They tend to be about a millimeter, give or take. And the neuron has various parts. So on the left side here, so I will indicate just one of them. So these are what are called dendrites that I'm circling. So these are projections, and this is, for our purposes, where the neuron takes in information. So these are the receiving parts of the neuron. And all the information will be brought together and added up and put together in an output for the neuron later. And we'll talk about how that works over the course of the week. But dendrites are sort of the input area of the neuron. And here in the middle, we have the neuron cell body along with the nucleus. If we remember from cell biology, the nucleus is where genetic information is stored. It's also where things like proteins get put together and assembled. Next, we have the axon, which is this long, spindly projection coming off of the cell body. And neurons only have one of these for our purposes. And then finally, at the end of the axon, we have what are called axon terminals, also called synaptic boutons, but we'll just call them axon terminals here. And so this is where information goes out. This is where information gets transferred to other neurons. And transferring information around is sort of how the brain works. That's what it does. So we need to bring in sensory information, process it somehow, recognize objects, and then send commands to our muscles so we can move toward an object or move away from an object. It depends on the sensory input. And again, for our purposes, information flows on this diagram from left to right. So information comes into the dendrites, gets added up together, and gets sent down the axon. And we'll talk about that axon portion of information transmission today. First thing, though, the brain is more than just neurons. So neurons are obviously very important. They're what process our information. But the neurons can't get it done alone. So there are special cells called glial cells They're also called neuroglia or just glia, and they come in several types. And they're actually far more common than neurons are. These are sort of the support system for neurons. And they're not crucial for our discussion for this class. Your book mentions them, so I'll just go over a few of the types, and a couple of them are important. So one of the types is astrocytes. And what do these do? Well, these do things like control blood flow. They also modulate synaptic activity, by which we mean electrical impulses that are sent down one neuron, and then they sort of jump a gap to the next neuron. And so they can modulate how that information gets transferred from one neuron to another. You also have microglia. As the name suggests, they're very small. And these do things like clean up the garbage around neurons and other glia. They have sort of an immune function. They'll sort of vacuum up invaders and destroy them. You also have things like ependymal cells. And these are cells that border what are called ventricles. We haven't gotten to the whole brain yet, but when we do, the brain has these sort of fluid-filled cavities in it. And so the ependymal cells border those cavities and produce what's called cerebrospinal fluid, or CSF. And that's just fluid that cushions the brain. So your brain is obviously sitting inside your skull, but it's not an air-filled cavity. It's not surrounded by air, it's surrounded by fluid. But it's not blood either. Your brain is surrounded by this cerebrospinal fluid that cushions it and moves nutrients around, gets rid of waste products. But it's different from blood. But there are glial cells that produce it, because it has to get recycled, has to get cleaned out and filtered every now and again. One of the important kinds of glia are oligodendrocytes. And what these do is they wrap axons with myelin. And why myelin is important, we'll talk about at the end of this lecture. But myelin is a fatty substance that wraps around the axons and makes them more effective conductors. And the gaps between these little waxy bundles around axons are called nodes of Ranvier. Those will become important at the end of the lecture. But just know that coating the axons with this fatty substance makes them more effective, and it's actually this fatty substance that breaks down in diseases like multiple sclerosis. It makes the neurons less effective, which is why MS patients have a harder time moving, because the myelin is being broken down. Also down here in the bottom left, you see a slice of a brain. So we've all heard the terms gray matter, white matter, and it's the myelin that makes white matter white. Without the myelin, it would just all be gray matter. And the myelinated neurons are myelinated so they can transmit information longer distances. But here in this picture, we see gray matter around the outside of the brain, so we can see it, for example, around in here. And the white matter, we can see these sort of branching areas where the inner portion of the brain is actually white matter, because those axons are myelinated. We also have things called Schwann cells, which are just the same thing as oligodendrocytes, but they myelinate neurons that are outside the brain. They have a different name. They work a little bit differently, but again, for our purposes, that distinction is not really important. The myelin, however, is important, and we'll see why later. Okay, so back to neurons for a moment. We've already seen the structure of the neuron. So how does information get transmitted? We know that neurons have to move information from the dendrites to the axon after integrating it in some way. But how does that information get moved? Well, it gets moved through something called an action potential. And this diagram in your book refers to it as the movement of an electrical impulse. And that's what an action potential is. It's a moving electrical impulse. And so what is an electrical impulse? Well, that gets down to the idea of what is electricity. And electricity is just the movement of charged particles. Now, in an electrical device, something we plug into a wall, it's electrons that are moving. But in neurons, there are charged particles called ions that are moving. But either way, as long as you have some charged particle, whether it's an electron or a whole atom, an ion, if it's moving, it's generating an electrical current. And so that movement of electrical current is something we can detect, and it's how neurons transmit information. They transmit it electrically. So for those that haven't had chemistry in a while, quick refresher. Elements are defined by the number of protons they have, not proteins, protons. So a proton is a basic charged particle. It's got a positive charge. Hydrogen has 1 proton, helium has 2, lithium has 3, carbon has 6. And so this is what defines what the element is the number of protons. Now for today, that's not as important as understanding that these atoms can have a variable number of electrons. Electron is the proton's counterpart. Proton is positively charged, electron is negatively charged. Now, if these two charges don't balance out, in other words, if the number of protons is not equal to the number of electrons, it becomes what's called an ion, which means the charge isn't even between the two, so the atom itself has a net charge. It's a little more positive or a little more negative than neutral. So if it has more electrons than protons, it becomes negative. If it loses electrons until it has fewer electrons than protons, then it becomes positive. And depending on what element you're talking about, there's a tendency for it to have a positive or a negative charge. We'll talk about which ions are important for today, but in the essence, that's all an ion is. It's an atom that has either fewer or more electrons than it has protons. So it has a charge to it. So how do ions behave? Why are ions important for our discussion today? Well, ions have two forces that are acting on them around a neuron, or anywhere, but today we care about neurons. Sometimes these two forces are aligned, sometimes they're in opposition, and the ions find sort of a balance point between these two forces. So the first of the forces is called diffusion. We've probably all heard of diffusion. Diffusion is just a way of saying that particles, and ions in this case, move from where they're highly concentrated to where they're less concentrated. So they move from where there's a lot to where there's relatively few. If you've ever been in a crowded room but it has a big open space, people more or less tend to diffuse to fill up the space. Well, particles are really no different. And so you'll have a high concentration area, and gradually, if there is another area that has very, very few ions, left to their own devices, the ions will move out to where they evenly cover the space. So that's diffusion. But there's a second force in place called an electrostatic force. And all that means is, and we've probably already heard this concept many times, is that positive charges repel each other, and opposite charges, as negative charges repel each other, but then opposite charges attract one another. So if you have two positive ions, as we see here, or two negative ions, it would work the same way, they tend to move apart. They're the same charge, and so they push each other apart. But if they're oppositely charged, those tend to attract one another. So positive ions tend to move toward negative ions and vice versa. So you have these attractive and repulsive forces based on the charge of the particle, of the atom. So again, we have these two forces, atoms, and repeatedly I'll say that atoms want to do this, or that ions want to do that. We want to avoid anthropomorphizing them too much, but that's just a convenient way of saying this is what they tend to do because of these two forces. So over here on the left, we have all these particles, and what these particles want to do is go from where they're concentrated to where they're not. Again, just a way of saying that's what they tend to do. Similarly, positive ions want to be apart from each other. Oppositely charged ions want to move toward each other. So don't let that make you think that ions have desires and goals. That's just our shorthand for saying this is what they tend to do. So a neuron has different concentrations of various ions inside the neuron and outside the neuron. The neuron is, in its simplest sense, a container. It has a membrane, it has sort of a wall that separates the space outside the cell from the space inside the cell. Now, they're both mainly water, but the difference is which ions are common where. And the ion reaches what's called an equilibrium potential. What does that mean? Well, it means, again, we have these two forces. So a couple of the ions that will be important today are sodium and potassium. Now, these are both positive ions. They both have a positive charge. So that means they're going to repel one another. Sodium doesn't want to be where potassium is, and potassium doesn't want to be where sodium is. But at the same time, the neuron has molecular machinery in place that keep a lot of sodium outside the neuron and a lot of potassium inside it. So what does that mean if you're a sodium ion? Well, it means that because there's so much sodium outside and almost none inside, that you really want to be inside that neuron. So if there's a hole in the neuron, which we'll call a channel, and we'll explain that in a bit, the sodium is going to want to flow into the neuron because there's so much of it outside, so little of it inside. But the thing is, there's already a bunch of potassium inside. And the potassium is positively charged like sodium. If potassium were negatively charged, well, everything about the environment would make sodium want to go in. There's not much of it inside, and it's got this negative ion pulling it in. But potassium's positively charged. So sodium wants to go in because there's relatively little of it, but it doesn't want to go in because there's already so much positive charge inside the neuron. So that's what we mean by an equilibrium. If we just let these two ions travel at will across the membrane of the neuron, they'll reach an equilibrium. Well, there will still be more sodium outside than in, and more potassium inside than out, but those two forces will balance out. And sodium will go in until the difference in the concentration is balanced by the amount of positive charge inside and outside. So how do we measure this? Is a big question. So we measure it with an electrode, or more accurately, a microelectrode. It has to be very small to pierce a neuron. A neuron is very small itself, and so the ends of these electrodes can be down to the millionth of a meter. So what are called microns or micrometers. So what happens is you pierce the neuron with one of these electrodes. So the electrode is sitting inside the neuron. And what you're doing is you're measuring a difference in the electrical charge inside and outside. So as I mentioned, you have at least sodium and potassium. There are lots of other ions around. But if you add up all the positive and negative charges outside, and then you add up all the positive and negative charges inside, you can measure the difference in charge. And that's described in volts, just like the volts on a battery. A battery is described in volts because that's a measure of the difference between the two ends of the battery. So here, a volt is relative to a neuron is a lot of charge. So they tend to be measured in millivolts, so thousandths of a volt. But regardless, what we're really doing is comparing the charge, the total charge inside the neuron, to the total charge outside the neuron. And if there's a difference, well, now we have that electrostatic force in play, that we have neurons want to balance out those charges. They want to be, if you're positive, you want to go where it's negative, and vice versa. So we have this difference in charge inside and outside, and that's going to drive positive charge inside for the most part. So which ions do we care about? Well, we've already mentioned some of the positive ions, which are called cations, not to be pronounced cations. It looks like it should be said cations. It's cations. So there are some positive ones, which is to say they have one fewer electron, one or more, fewer electrons than protons. So things like sodium, we've heard of, it's half of the molecule salt that we all ingest every day. Potassium is another positive ion. As we said, outside the cell, sodium is very common. Inside the cell, potassium is very common. We also have things like calcium, which is not going to be very important today, but the next lecture it will become more important. We also have negative ions, which are called anions. Again, not anions, it's anions. And so these are things like chloride and proteins, which, again, not important today, but next lecture they will be. And we have what are called ion channels, which are holes in the neuron's membrane. It's a way for ions to move across from one side to the other. Now, some of these ion channels are always open. So, for example, in this diagram, we have this potassium channel. It just sits there, and it's always open. So it lets potassium out, because there's a lot of potassium inside, not much out. And so potassium tends to go out of the neuron. Now, it turns out there's a little molecule on neurons that it's constantly pumping potassium back in and sodium out to maintain those concentration gradients. It wants to keep a lot of sodium out and a lot of potassium in, because then it's ready to fire an electrical impulse, an action potential, whenever it needs to. So some of these channels are always open, but as we'll see, some are what are called voltage gated. What does that mean? Well, it sounds fancy, but all that means is they're closed until the difference between the inside and outside charge of the neuron is sufficient to open the channel. And then it's open for a little while, and then it closes again. So it just means that it's not always open. It depends on the context. And we'll see this is very important because action potentials aren't always firing in a neuron. They're selective. And in fact, action potentials only exist because of voltage-gated channels. Okay, so we've already mentioned action potentials, which are just electrical impulses that the neuron uses to transmit information. And we just talked about all the ions that are in and around a neuron. Now, as it turns out, for the action potential, really only two of these are important, and those are sodium and potassium. So these are both positive ions, and what happens in an action potential is you see a rapid change in the membrane potential. It's often called a spike, and this spike is this rapid change in the membrane potential that travels down the axon very quickly. And so what we're going to see is that this change of potential results from sodium coming into the neuron and potassium coming out. But these things occur at different times. And so we're going to talk about the sequence of events that constitute an action potential. Now, when a neuron isn't firing, it's just at what we call rest. So it is at its resting potential. And all that's happening then is that these particular potassium channels are open. So they're letting out a little bit of potassium. Remember, potassium is really common inside the neuron, not so much outside, and so potassium tends to move out of the neuron when it can. So with these open channels, a little bit of potassium flows out, but the neuron has a molecule or a set of molecules in place that are constantly pumping in potassium and pumping out sodium. And that's how the neuron maintains these concentration gradients, how it maintains a lot of sodium outside and a lot of potassium inside. So it's just sitting there at its resting potential, a little bit of potassium going out. And then, if something changes that membrane potential, we can do it artificially with an electrode, or if sodium flows into the neuron nearby, then suddenly we have more positive ions inside the neuron. And what is that going to do? Well, more positive ions inside the neuron means the membrane potential isn't quite so negative. Right? Remember, normally we have more negative charge inside than outside. If we move some of that positive charge into the neuron, then that membrane potential isn't so negative. And that's called depolarizing the neuron. So when positive charge moves in on this part of the curve, it depolarizes the neuron. In other words, it moves it closer to zero. Normally the membrane potential is negative. Positive charge flows in. That membrane potential moves closer to zero, so we call it depolarization. It's not quite so polarized. Now, once it hits a certain threshold, once it gets depolarized enough, sodium channels start opening up. And of course, there's lots of sodium outside the neuron, and there's lots of these sodium channels. So as they start to open, sodium starts coming into the neuron. There's a lot of sodium outside, very little inside, so sodium comes rushing in. Well, that's going to make the membrane potential even more positive. We have all the sodium coming in, and so now, and it's coming in very rapidly because these are voltage-gated sodium channels, they're sensitive to the membrane potential. So the more positive it gets, the more open. See this positive feedback system. So sodium comes in, opens more sodium channels, even more sodium comes in, opens more and more, until they're all open and sodium's coming in as fast as it can. And it brings that membrane potential up to around 50 millivolts. So in fact, at that point, there's more positive charge inside the neuron than outside. But those sodium channels don't stay open forever. They have sort of a deadline. And after that, they start closing. They can only stay open for so long. And at that point, once it's positive enough, then these voltage-gated potassium channels open. And remember, potassium wants to go out of the neuron. And so it's going the opposite direction of sodium, but it's also positively charged. So now these potassium channels start opening up, the sodium channels are closed, and so all this potassium starts rushing out of the neuron, which means now there's more positive charge outside than inside, which is how it was before. So potassium starts going out, sodium is at this point stopped flowing, so all this potassium goes out, brings that membrane potential back into negative territory, and then eventually the potassium channels shut down. So they close. And then those molecules that maintain those concentration gradients, pumping sodium out, pushing potassium in, combined with a little bit of potassium that's always leaking out of the neuron, bring the neuron back to its resting potential. And so that's the state we have at the end here, with just these small number of potassium channels open and letting a little bit of potassium out. So that's what the action potential is. The neuron gets a little bit depolarized, then those sodium channels that are voltage gated sense that change in the membrane potential, they start opening up. Lots of sodium comes in, opens up all the sodium channels until eventually they shut down. And then potassium channels open, and now positive charge is rushing out of the neuron in the form of potassium. So we see this quick increase in the membrane potential and this just as quick decrease. And then it returns back to its resting potential and it's ready to fire again. Okay, so how do we conduct an action potential? Well, we just talked about how an action potential works at a particular location, at a single location. And the thing about neurons is because of the dynamics, we're not going to get into the details, of the way those ion channels open and close, the transmission is one way. So it doesn't start going down the axon and then starts backing up. It only goes one way because once a particular area of the neuron is fired as action potential, it sort of shuts down for a little while. It has what's called a refractory period where it can't fire again. So the action potential travels down the neuron one particular direction. Now in a normal unmyelinated axon, it moves about 10 meters a second, which sounds fast, but relative to myelinated axons, as we'll see, it's really not that fast at all. So what happens? Well, if an action potential fires, imagine you're the next location down the line, so to speak. And action potential fires, well, all the sodium has just come into the axon next to you. And so that sodium has a positive charge, and it's going to depolarize your section of the axon. So it's going to depolarize all the sodium channels that are nearby, and that's going to open up those sodium channels. Sodium is going to flow in there, and of course that's going to depolarize the next section. So the positive charge will propagate down that way, and that's going to open those sodium channels. And so then sodium channels will open, more positive charge flows in, and so it just keeps on going down the axon because the positive charge flowing in at one location opens the sodium channels at the next location. So that's how an action potential moves down the axon. Now, if there's myelin around them, they're faster. And why are they faster? Well, the coating the axon in myelin has the effect of sort of insulating it. So sodium, once it comes into one of the nodes of Ranvier, which is just the open space between myelinated sections, sodium comes in here, and now it has nowhere else to go but down the axon quite a ways. So there are no outlets along the way because of this coating that let sodium out or let potassium out, really, to compensate for the increased positive charge inside. And so what does that do? It concentrates that positive charge until it gets to the next node, and now that's going to open up all these other sodium channels. Again, sodium will come rushing in, and that'll propagate down to the next section of the axon. So by insulating these intermediate portions of the axon, it really makes that change in charge, travel that much faster. And this is what's called saltatory conduction. Saltatory, not from salt, but from the word to jump. So the change in potential is really jumping from one of these nodes to the next one. And it happens very, very quickly. This sort of impulse can travel 150 meters a second as opposed to 10. So it's a much faster impulse. You can transmit information much faster, which is great for things like reflexes or muscle movements. Okay, so that is it for this time, talking about neurons. Next time, we'll look at another aspect of neuronal function, and that is how neurons transmit information from one neuron to the next. And they do this at junctions called synapses. So first we'll talk about synapses physically, what they look like, what their structure is like. Then we'll talk about transmission, so how information passes from one neuron to the next. And then we'll talk about neurotransmitters, which are the chemical messengers that allow one neuron to send information to the next neuron.